Terrain is likely to be the main object of your outdoor worlds. It defines the environment, and therefore the impression your project makes, be it a game or a simulation software. The primary terrain system in UNIGINE, Landscape Terrain, supports asynchronous large-scale data streaming, adaptive hardware tessellation, and layer-based workflow to meet strict requirements for professional-grade simulation software. Manual creation of an arbitrary terrain from textures and via sculpting is shown in the Landscape Terrain video tutorial. In this tutorial, we're going to replicate an exact real-world location, a typical task for simulation software development. For such tasks, UNIGINE Engineering and Systems offer you the Sandworm Tool, enabling you to create terrains based on georeference data and populate the world with procedurally generated props. We are going to give you the most comprehensive guide on settings and terrain generation process. First things first, to generate a terrain, you need raster and vector data sources containing georeference and projection info. These can be offline data sources stored on your hard drive, such as satellite orthophoto and aerial photography results. As a rule, these sources have georeference and projection information embedded, as well as data prepared using GIS software, such as ArcGIS, Global Mapper, and so on, and online data sources, TMS or tile map services. Sandworm supports all widely used data formats. To follow this tutorial, you can use the Georeference Terrain Generation Asset Pack, available on the Asset Store and containing ready-to-use assets. Let's also add Procedural Generation Assets, a pack of various ready-to-use materials for buildings. Make sure you have downloaded the required asset packs and then create a new project. Choose the desired API and decide whether your project needs double precision of coordinates. Basically, if your virtual world is going to take more than 10 by 10 kilometers, you will need to select the double precision option. Otherwise, the float option will be fine. Let's also include the downloaded asset packs in the project. Now you can launch the editor. We recommend to disable microprofile for this session, for the sake of performance. Open the Sandworm tool and create a new project. You can specify its name, path, and the working coordinate system. We just keep the default settings for now. Click Next and wait for the Sandworm window to load. The map panel represents the main workspace and displays the world map and imported geodata sources. You can zoom the map using the mouse wheel and pan the view by holding the middle mouse button. The toolbar at the top lets you switch between the map modes. The pan mode is currently active, meaning you can pan the view using the left mouse button as well. The other mode is intended for selecting and editing data layers. There are also the zoom buttons. Mouse cursor coordinates and the current coordinate system are shown on the right. We'll get back to them later. Note the tips panel below. It shows hotkeys for the current mode and the map scale that helps you estimate distances as you roam across the map. The Sources panel is where you specify data sources for your terrain. Terrain layers, a raster data sources, and maps that define the terrain surface. They are elevation or height, a single channel height map, imagery or color, a surface color map, and mask, an auxiliary texture treated as a mask for various purposes, such as land cover, for example. Objects are vector data sources used for generation and placement of various objects on the terrain surface. The Parameters panel shows the parameters of the currently selected data source, just like the Parameters window of the editor. The last stop is the Generation Settings panel, where you specify all necessary output settings before pressing the Generate button. For now, it is unavailable, as the hint tells us we need to add terrain sources. Let's get to it. To add a terrain layer, click plus next to the desired type. You can choose between using a georeferenced image, resources stored on your computer, or tile map service, an online source. Let's start with the georeferenced image option. Here, we can use one or several assets imported in the UNIGINE project, as well as external files stored somewhere on the hard drive or shared network storage. There is no need to import terrain sources that are quite heavy. One of the most widespread raster geodata formats, GeoTIFF, is the common raster TIFF format with georeference data embedded. The industrial ECW format used to store aerial photography and satellite imagery is also supported. Sandworm adopts GDAL to support various widely used raster and vector geospatial data formats. All supported formats are marked built-in by default. It's recommended to use 16 and 32-bit textures for the best height map quality and accurate terrain surface. Select the elevation image from the georeference terrain generation asset pack. Now let's click Preview to generate its preview on the world map. You can define the area to be considered in terrain generation by adjusting boundaries for the layer. Simply click Edit. As you can see, we have switched to the editing mode, and we can select layers by clicking on them. By default, the boundaries enclose the entire layer. You can adjust them to fit your needs. Add new points with Alt plus left click and remove them via the right-click menu. You can also enclose the preview area or delete the boundaries to use the layer entirely. Finally, click Create Elevation Layer to apply settings and create a layer. Let's add imagery layers the same way. The asset pack includes a tile set with imagery data, so select all the tiles and click OK. Now we go to Online Tile Map Sources. Note that internet connection is required. Add a new imagery layer and choose the TMS source type. In the drop-down, you can select the tile map service to use. This list is likely to be empty for you now, so let's open it for editing. The table lists all available TMS sources for management, with a web address and an alias specified for each one. You can add as many sources as you need. There are many tile map services available, usually with paid access to data, but you can find open services too, such as OpenStreetMap and Madbox. Tiled maps are based on the spherical Mercator projection, also known as web or pseudo-Mercator, and the fixed exponential tiling profile, so any tile can be easily retrieved based on geographic coordinates and a zoom level. Almost all open source and commercial providers follow this standard to ensure compatibility. However, the features and data format of each TMS you use should be carefully considered. Once registering in such a service, you will get the URL that should have X, Y, and Z tile coordinates embraced into curly brackets, where Z indicates the zoom level while X and Y are horizontal and vertical tile coordinates calculated by Sandworm. Sometimes URL should include an access token, but the sources that require authentication via credentials are currently not supported. You can also edit the list of TMS sources in the JSON configuration file in the project subfolder. Changes will be available when adding a new terrain layer. After configuring TMS sources, click Save to make them available in the list. Choose the desired source and specify the boundaries for tiles to be loaded. Also, set the desired zoom level defining the final data density and the number of tiles loaded. Values from 10 to 16 are usually fine for a bird's eye view. The hint will tell you the size of the data to load. Generating a preview is optional, but might come in handy for evaluating the used data, so press Preview to download tiles and generate the layer's preview. You can experiment with different zoom levels and sources. Then create a layer. If something goes wrong, you will get a black area. Check the console window for details. You can add elevation and other sources the same way. It is important to use the corresponding TMS sources for the layer types. Single-channel images for height and RGB images for color. All added layers of data are displayed in the Sources panel. Any layer can be turned off if you don't want to use it for terrain generation. The context menu enables you to focus on the selected layer. Move the layer to background and foreground. This won't affect the result and is only intended for convenient interaction with layers. Selected layers are moved to foreground automatically for convenience. Generate preview for the layer. Here you can also remove the layer, recheck layer properties, source coordinate system, data density in meters per pixel, and boundaries. To rename a layer, double-click on it. Settings for the selected layers are always available in the Parameters panel. Well, we got several data layers of different size and density. There is an inset of higher resolution in the middle, representing an area of interest. This can be useful for flight simulators, where high details are only required for areas around airports. All layers are reprojected to the current working coordinate system. At the moment, UP's G4326 is selected. It is the authority code for WGS84 and APS-G geodetic registry. This is one of the most popular coordinate systems used, for example, in GPS. It is a geographic coordinate system that covers the Earth entirely, so the coordinates are expressed in degrees of latitude and longitude. You can choose the option that best fits your data set from a large set of supported coordinate systems. Sandworm supports geographic and projected coordinate systems. Geographic systems are most convenient for data preparation and alignment. However, they are not suitable for evaluation of the final terrain representation when projecting data to a flat surface. To generate a terrain, a projected coordinate system is required, which transforms coordinates from degrees of latitude and longitude into actual distance units, meters, feet, and so on the surface. The cartography problem comes from the impossibility to represent the Earth's surface on a flat map without introducing distortions and directions and distances. There is no universal projection meeting all the requirements. A large set of projections enables you to choose the most suitable one for your working location with minimal distortions, taking into account the standards used in geodesy. You can find the desired system by its EPSG authority code or name, as well as select the coordinate system used in the loaded data sources in the source coordinate system section. Let's choose the pseudomercator, used in most popular WebGIS services. All layers in the world map will immediately be transformed to the new coordinate system. This is a projected system, therefore the coordinates are now displayed in distance units, meters in our case. If necessary, you can turn on auto reprojection to geo-coordinates with this button. In this case, the projected coordinates will be transformed back into geographic ones based on the projection formula, resulting in small misalignment with real geo-coordinates. A projected representation is suitable for evaluation of the resulting terrain and compatibility of the data set with the selected coordinate system. However, for data adjustment, a geographic coordinate system is recommended. EPS G4326 is a fine option for beginners. Though we have set up all data sources and the hint tells us to specify the output projection. Click it to go to the generation settings. The first one is the terrain type that defines the set of settings and features available. There are two options for terrain simulation in UNIGINE. The main landscape terrain system, which supports layer-based workflow, adaptive tessellation for sub-millimeter density and efficient asynchronous data streaming. The legacy global terrain system, which has a number of problems but supports simulation of Earth's surface curvature. In this video tutorial, we will use the landscape terrain system as the recommended one. Global terrain is to be considered separately. The expert area section enables you to set the boundaries for all data sources and define the final shape of the terrain. Area size shows the area of the selected region. You can also define alignment of the terrain relative to the origin of coordinates. Uncheck to calculate origin, automatically flag and specify the desired geo-coordinates to be treated as the origin. If you enable the flag, the origin will automatically be set to the center of the selected region, placing the terrain in the center of the virtual world. In the editing mode, you can select and control the boundaries of the expert area as well. After the boundaries are adjusted, you can freeze them by enabling the block expert area to change its flag so the expert area will not interfere when you edit layers. Remove the boundaries to generate the terrain entirely. The next section, Data Types, enables you to choose data types for expert terrains, raster data, and vector-based objects. It is very convenient as you can save time, for example, when adding roads or buildings to your generated terrain without rebuilding the terrain itself. In the projection section, we should specify a projected coordinate system for terrain. If you are new to geographic information, EPSG 3857 is a fine option. The pseudo-Mercator projection covers most of the planet, but has strong distortion in areas away from the equator. You can choose an appropriate projection using the third-party epsg.org service. Go to the Map Search section and outline the required region. In our case, it is the surroundings of the Swiss city of Winterthur. Upon clicking Search, the service offers a choice from the list of the most suitable projections for this region. Here we should find a projected coordinate system. The description will give you details and coverage information, as well as the authority code that you can use to find the coordinate system in the Sandworm Tool. Selected projection should cover the working area entirely. Otherwise, the portions outside the coverage area will be lost and will not be included in the final terrain. However, increasing the working area size reduces the chance to find a suitable projection and increases the probability of having a strong distortion of distances and angles. Some coordinate systems have an orientation that is different from north up and east right. When using such a projection with the source option selected in the coordinate system parameter, the output terrain will be oriented accordingly. Navigation in the virtual world may become inconvenient, so you can change the value to UNIGINE World to align the terrain according to the standard axis in UNIGINE. The north corresponds to the Y+ axis and the east to the X+ axis. It is important to keep in mind that automatic orientation is not compatible with projections having a different orientation order. For example, northwest, because this produces an inverted result. In such cases, it is better to stick with the source option. The next section is the quality of the final terrain. You can decrease the quality slider that determines the portion of the source raster data as percentage to accelerate terrain generation with reduced quality for fast iterations during development. Landscape terrain supports compression of graphic data to save disk space on your computer. You can choose between lossless and lossy compression methods, or configure the compression process to fit your needs by choosing the custom option. Here, you can choose a compression algorithm. We recommend the default AU method and toggle lossy compression for terrain components, opacity, albedo, and masks. Do not use compression at all, or use lossless compression at the development phase. To avoid losing the source data quality, lossy compression should be used only for the final result to minimize hard drive consumption. You can find more details in tooltips for parameters and in the documentation. Generation of a high-quality terrain is a heavy task. You can speed up data processing by means of distributed generation using the full power of your computer cluster. We are going to consider this later. The last stop is the output settings. Before we start the generation process, we should specify the world for the terrain and the output directory for generated assets. By default, it is a subfolder named after the project, as well as the location to store cache, improving generation speed. We suggest clearing the generation cache after all test runs before the final generation of the terrain in maximum quality to prevent any unlikely errors in the data. Also check locations for editor and terrain compression cache. For best generation performance, it is recommended to keep these service directories on high-speed storage devices, such as SSD. Make sure the drive has enough free space. Let's save the project with all the settings. Now we can start terrain generation. Click S in the confirmation window and wait. Note that the generation process may take a lot of time depending on the play area size and density of the data sources used. Upon completion, you can close the Sandworm window and check the result. A new terrain has just been created. Switch to the new Sandworm camera to preview the terrain from above. You may also need to increase the far visibility distance in the camera settings and the terrain rendering distance in the render landscape settings. By default, this value is set to 30 kilometers, beyond which terrain is not visible. Set the desired value according to the size of your location and the typical height at which you will observe it. In the World Nodes window, we can see the new object landscape terrain and two landscape layer maps of different density, representing a distant level of detail and a high density inset. Sandworm merges layers of the same data density into a single layer map for convenience. Each layer contains a bounds node with its boundaries for simpler navigation at large distances. You can edit any terrain component manually. Switch to the landscape paint mode. Select a terrain layer, the component, heights, albedo or masks, a brush, blur or eraser tool, and a brush with a certain hardness and shape. Colors of geodata rarely require manual editing, but it may be necessary to adjust heights based on the requirements of your project. The list of hotkeys will help you quickly get familiar with the tools. Let's switch to the normal mode to save changes. Remember that if you choose to regenerate the terrain, let's open the Sandworm project again by double-clicking it. Your changes to terrain components will be lost, so they should be made last. Instead, it is better to make changes on a separate landscape layer map so that the generated and manually edited layers do not affect each other. You can find out more about brush-based editing of landscape terrain in the corresponding video tutorial.